Hello, everyone, and welcome to this session on the power of data to create greener futures. My name is Gavin Shaddock, and I am Chair of Data Science and Statistics at the University of Exeter, and also the co-director of a newly established joint research centre in environmental intelligence with the Met Office. We've got a really interesting and packed agenda this afternoon with a keynote speech followed by some short presentations, a panel session, and then an interactive workshop. And it is my great pleasure to hand over to Laura Fleming, who's Director of the European Centre for Environment and Human Health at the University of Exeter and Professor of Oceans and Human Health. Over to you, Laura.
Thanks very much, Gavin. I'm really excited about this session on using the power of data to create solutions for green futures. I'm a physician and epidemiologist, and as you know, Gavin, I've been involved in this area for about 30 years. And I think what a lot of people don't realize is that the whole aspect of how climate and other environmental change is affecting human health is actually fairly recent. The public health and medical community has not really embraced this area until probably the last decade. So there's a huge opportunity there for us to work with people who are experts in big data and environmental intelligence around the connections between our health and the health of the environment. I think there's opportunities both in terms of interdisciplinary research and training. From my point of view as a physician epidemiologist, learning new techniques and approaches, being able to have the opportunity of linking with new data so that we can truly understand how our health depends on the health of the natural environment. And so as such, I'm really excited at how the University of Exeter, under your leadership and with many colleagues, it now has these amazing collaborations with the Met Office, with the WHO, the World Health Organization, including the Joint Center, the Center for Doctoral Training in this area, and collaborations also with the Turing Institute. And I think some of the people that will be speaking later in this session will illustrate some of these amazing collaborations and the potential. So now I'm actually going to introduce our brief keynote address. Sophie Gumi is a technical officer in the Department of Environment, Climate Change and Health at the World Health Organization, the WHO. She's leading the WHO's work on evidence synthesis, capacity building, and monitoring of ambient air pollution exposure and related disease burden. And I believe that you and Gavin are going to be doing a really interesting short keynote. And thank you for this.
Thank you very much for everyone. Thank you. Good afternoon. First, thank you very much for the invitation. This is a pleasure to be here. Indeed, we will share with Gavin, so I will try to be as quick as possible given the time given. So you have introduced me. I'm working at the World Health Organization in Geneva, and I will start with presenting a quick snapshot on the WHO's activities on air pollution and health, and then introduce how we work with data, and then I will leave it to Professor Shaddock to go on with the scientific side of the presentation. So, first of all, I would like to remind that WHO is a secretariat and our employers are the ministries of health of the member states, and there are 194 of them. WHO is organized in such a way that we have headquarters in Geneva, but we also have 6 regional offices, and we have about 150 country offices, mostly in low and middle income countries. In general, and more specifically in our case in environmental health, we collaborate with a wide variety of partners. We collaborate closely with academia, obviously, and this presentation is a good example of it. We work also with civil society organizations. We work with UN agencies, with national institutions. And this slide provides a summary of our activities in headquarters, where the focus is on global normative and standard setting work, and also data-related activities. So the first big chunk of work we are involved in is about leadership in general. So we work on advocacy. We launched 5 years ago a raising awareness campaign called Breathe Life, which was targeting the general public, healthcare professional, and cities. The reason why we targeted cities was that another important role we have is to leverage the political support. So to do so, we also organize global conferences, we established a health and energy platform of action, and we are also engaging with the non-communicable disease community now that air pollution has finally been recognized as a risk factor for non-communicable diseases. A second big important role for WHO is to monitor and report on health trends. So we, since decades, WHO has been publishing statistics on health and also on risk factors. Since 2015, WHO is custodial agency for many different sustainable development goal indicators, mainly related to health, but also outside of the health goal. For instance, WHO is responsible to report on mortality from air pollution, air quality exposure, and on access to clean household fuels, which is a proxy indicator for household air pollution exposure. I will come back to this function in a later slide. A third stream of work is on normative and standard setting work. Since decades, WHO is regularly issuing air quality guidelines, both for indoor and outdoor environments. And in the case of household air pollution, there are even recommendations on the implementation of the guidelines. Technical support to countries, this is an important part of our work as well. And this is not only headquarters, but this is more for regional and country offices, but we are also pulled in those activities. And our role in headquarters is mainly to synthesize evidence and tools development. Finally, WHO is engaged in capacity building activities. We have been together with partners supporting the development of various tools to assess the health impact of air pollution or to assess the health and economic evaluations of various interventions. And finally, we are also currently developing training material for the health sector on air pollution and health, because unfortunately, this is not yet really taught at in the curriculum. Next slide, please. As this slide indicates, WHO is a science and evidence-based organization. In that respect, it is quite unique within the UN system, with a few exceptions, like maybe the World Meteorological Organization. So one of our key products are the WHO air quality guidelines. Since the 60s, WHO has been convening experts to review and discuss the impact of pollutants on health. And the first guideline was published in the late 80s. The development of WHO guidelines has evolved over time, and it is now today a very lengthy process that uses standards and specific methods to ensure that the guidelines are free from bias and meet public health needs. A systematic review of the scientific literature is conducted and evaluate the adverse health effects from exposure to selected pollutants for relevant averaging time and in relation to critical health outcomes. The guideline thus contains evidence-based recommendation on concentration limits for a given pollutant. And we also, acknowledging the fact that some countries may not be able to reach the guideline, we also propose interim targets so that countries can really adapt their standards according to their economic and development context. Next slide, please. Having data is great and necessary, but if we don't agree on data, it is not so useful, and the debate is stuck on the data issues and we cannot move forward. So we have really been facing this a lot on air pollution and health issues. So therefore, science policy processes are therefore very crucial to ensure a good use of the data so that we can advance on the policy agenda. On air pollution and health, there are two excellent examples of such framework. The first one is the Convention on Long-Range Transboundary Air Pollution. This convention is hosted by the United Nations Economic Commission for Europe. It was created in the late 70s, when Scandinavian countries were suffering from acid rain originating outside of their national boundaries. And since its inception 40 years ago, the convention has developed into a successful regional framework for controlling and reducing the damage to human health and the environment caused by transboundary air pollution. There are 8 protocols for different pollutants, and the convention provides also access to emission measurement and modeling data and information on the effect of air pollution on ecosystem, health, crops, and materials. A second very important process is the Sustainable Development Goals, or SDGs. So in 2015, the United Nations General Assembly adopted the 2030 Agenda for Sustainable Development. And on its art, there are 70 Sustainable Development Goals and something like 230 indicators that really call countries on monitoring and trying to really move towards a better planet. So the entire process is led by the United Statistics Division. It's really data-driven. And every indicator is really negotiated. Every methodology used to derive the indicator is negotiated. So once the indicator is accepted, this is really key, and this is really important, because then they do not spend so much time arguing about it. So this SDG framework is really an important framework because then really countries cannot, as I said, cannot downplay it afterwards once it's agreed. And WHO, we are responsible for this. So 3 of those indicators on air pollution, and this was a really key achievement because it was the first time that health was becoming a key player in the discussion from a transsectoral action. Next slide, please. And I think now I will give the floor to Professor Shadek, who will present how we have been collectively working together. So over to you, Gavin. Gavin, we cannot hear you.
Thank you, Sophie, and thank you for the lead up to the work we've been doing with the WHO and Sophie's team over the last many years now. So I really just wanted a brief summary of how we've been estimating air pollution for health burden analysis. There's a need for accurate estimates of exposure to air pollution at global, national and local levels, and in particular for every country. And that's also needed, as Sophie just said, for tracking progress against the SDGs. And of the 93 environment-related SDGs, UNEP suggests that InterVish data exists to assess progress for 68% of them. And where data is available, it's often out of date. And there's a real problem with lack of disaggregated information. In the case of air pollution and health, we can see the problem on the right-hand side. This is a map of the world showing the location of PM2.5 monitors in the WHO's ambient air database. And you can see there's lots of information in North America, Western Europe, increasingly China, and actually India as well, if we count PM10. But there are large areas of the world for which there's just no or very little information that we can use to assess progress against the SDGs and to assess the health impacts of air pollution. I'll speed up a little bit, but what we've really been doing is to make use of other data sources. And there's a rapid increase in number of variety of data sources. I'm actually in Goonhilly Space Station in Cornwall at the moment at a satellite applications conference event associated with G7. And there's an awful lot more information that's out there that we can relate to air quality. We can estimate air pollution from aerosol optical depths. We can use land use information, but we do have to bring it all together in a coherent way. And to that end, the WHO established the Data Integration Task Force, an interdisciplinary team covering public health, atmospheric modelers, epidemiologists, statisticians, data scientists, computer scientists, remote sensing experts, to really work out how best to use this increasing information to get to that goal, which is to really understand the exposures and the quality of the air breathed in by people all around the world. And the result was the Data Integration Model for Air Quality, or DMAC. And technically, this is a Bayesian hierarchical model. It has a whole series of calibration equations between those different inputs. And the result is we take the ground monitor map on the left, we integrate that with satellites, chemical transport models, land use information, population information, and we can then produce estimates of PM2.5 air pollution on a high resolution grid covering the entire world. And crucially, not just estimates at any one location, but also we understand, or we have estimates of the uncertainty associated with those estimates, and we can feed those uncertainties through to the calculation of health burdens. And this is the approach used to calculate SDG indicator 11.6.2, annual mean levels of fine particulate matter in cities, and also as the basis of the WHO estimation of the burden associated with ambient air pollution, which currently stands at around 4.2 million premature deaths each year. And with that, I will hand over to Sophie to cover a few key messages.
Thank you, Gavin, for this, and all your team, of course. So yeah, just to summarize, an important role that WHO has is the convening power and the ability to really convene all the different experts from various disciplines. This is really key, because then you can really all sit down at the same table and agree on data and methodologies. And this links to my second point, is they agree on clear criteria for data input and methodology. So those two parts, they are very much important, because we have seen, I'm sure Gavin can also testify on that, how sometimes skeptical countries can be, which they can be national government or local government. I mean, you probably all know that as well. But this is really very important to clearly define this. My third point is that to build trust on the data. So on air pollution, the landscape has changed dramatically in the last 10 years. We have more and more data. There is more and more interest on the topic. So there are a lot of new data for various reasons, and also citizen science, etc., and big data. So it's very important to build trust in the data, because this takes time. So I think in the end, just to conclude, also a good communication and a good balance between the scientific part and all the different details, and trying to convey the key messages. This is key. But to conclude, I would just like to say thank you very much to University of Exeter. We have been collaborating greatly, and I hope it will continue in the future. Over. Kevin, you're still muted.
Thank you, Sophie, and thank you for those kind comments. It's been an absolute pleasure working with the WHO, and long may it continue. We have probably around 2 minutes, I believe, timing-wise, in which we could maybe see if anybody has any questions. If you do have questions, please put it into chat. Or I guess this might be an opportunity if anybody on the any panelists have any question. Oh, there's a question in the chat. What are the key actions that you think would make the most difference to improving air quality around the world? Over to you, Sophie.
That's a difficult question. If I knew the answer, we will already be a bit better. I think this is something that has to. There is no one answer, and there is no one ingredient in this recipe. I think there are a lot of different things. So I think data issue is a first key. I mean, key. First, we need to have data. You need to have data you trust. Second, you need to have a process. You need to have a lot of more information also on the interventions, and how to measure the impact of interventions on health, namely on health, and also on reducing emissions. And third, I think there is also a component that is linked to governance in countries, because you need to have a good communication between the different entities within a government to make action, and to have those actions actually implemented. So yes, I think we have successful examples. We have countries that have been successfully reducing their emissions, but it took decades. So there is no quick answer, there is no quick fix. So I think the better we start doing something, the better it is. I hope it addressed the question a bit.
Very good. Thank you so much, Sophie. Now, as I said earlier on, we do have a rather packed schedule of exciting things this afternoon, and we've now reached the end of our first session. And my understanding is that we're now going to move to a series of presentations on different aspects of work being done in the area of environment and climate change, using data at the University of Exeter.
Hello, everyone. My name is Professor Karen Morrissey, and I am an Associate Professor in Population Health in the European Centre for Environment and Human Health. And I have been using big data in its truest sense for all of my career to date. So, ever wondered how big data can help you maintain and manage your home health and well-being? The SmartLine project aims to connect researchers, households, organizations, and businesses to understand how everyday digital technology can be used to address the health and well-being needs of people in their homes and communities. Already, our research has found that things like fuel poverty not only impacts people's physical health, but also their well-being. We're using big data in its truest, biggest sense to further understand the impact that this has on all aspects of people's lives. For example, as we get to grips with the data, we're also starting to understand people's behaviours within their home and the impact of their behaviours on their health. For example, using data on water, electricity, and gas usage, we were able to measure how household activity changed during each of the COVID-19 national lockdowns. We believe that helping people to see the relationship between their home and environment and their personal health and well-being through the power of big data has the potential to make people and their homes happier and healthier places to live. Thank you very much.
Open science is the practice of making research results and data accessible to anyone and everyone. At the University of Exeter, we believe the sharing of data is essential in the tackling of climate change. For example, data linkage across the agricultural industry can help greatly reduce the environmental impact of breeding, farming, and crop production by using field data as a global indicator. However, indiscriminate and unregulated data openness in this realm is socially damaging. Data provided by legitimate research contributors, such as breeders, farmers, and their communities, can be exploited without acknowledgement or reward. At eGenis, we believe data should be shared lawfully and ethically, in a way that is fair to everyone involved, to build trust, include diverse contributors, and voice multiple perspectives. By investigating intelligent openness, we can then foster a culture of data exchange and better, more responsible, open science.
Hello, my name is Sabina Leonelli. I'm a professor of philosophy and history of science at the University of Exeter. And today I want to talk to you about what data can tell us about developing coping strategies for a rapidly changing planet. And what this means is thinking about how do we use data. And in the case of my research, we're looking particularly at data of relevance to agriculture, data about crops, data about plants, using this data as global resources. And this also means making data widely available. This is the notion of open data, making this data available so that anybody can use them in whichever way they want. Data are arguably a common good that can and should be harnessed for the survival of humans and of the planet. However, data can be highly diverse, difficult to actually interact with. There's very different types of data sources, different data formats, and most importantly, there are different types of cultures of data exchange and data sharing that can be across scales, across national borders, and across the private and the public domain. It turns out that, in fact, having data fully open, especially data of relevance to agriculture, can, in fact, hurt people and hurt the planet. This is because making data open is difficult to reconcile with the rights of indigenous groups, for instance, but also farmers and local breeders. And also, there is a huge amount of privatization of data from plant-liars and farming instruments, for instance, in the agrotech business. There is no really clear intellectual property framework around this kind of data, and regulation around data sharing varies enormously across the globe. So we urgently need some agreements around the different stakeholders in this field for the sharing, the access, and the reuse of data. The big question that all of this raises is, if we talk about governing this data, who is responsible for this and who should establish rules for data governance? This is the kind of question that we are asking in a project at the University of Exeter, which is done in collaboration with the Alan Turing Institute, where we're looking at how making open data fairer to everybody involved can actually help mitigate climate change. As part of this, we are looking, for instance, at ways in which data can be properly curated, taken care of, so that it can really foster a critical reuse, so that people don't just take data for granted, but they really think about how data can be reused in ways that are fair. Building responsible practice into a technical specification of data infrastructures, databases, is not just a question of adding ethics at the end of this research, but really thinking about it all the way through. Involving data providers, again, in the research process so that we can get their voices heard in the research process. And of course, encourage a wide-ranging debate over why we are reusing this data. What are the overarching visions of human development that we want to promote with this kind of research? One of the things that we have observed is that the conditions for trustworthy data sharing in this field vary enormously. They, of course, involve technological issues, having the right software, the right hardware, using the right databases, but they also involve a mix of relevant skills. And this can vary between skills from data scientists and skills from domain experts, and also farmers and breeders. We need appropriate policy and governance norms to define what constitutes fair data use. And most importantly, we need to have a framework for the ethics and the accountability of data sharing in this domain, a framework that acknowledges the provenance of data, that allows to allocate responsibility for the reuse of data, and help us to identify the gaps and who may be excluded from these transactions and should in fact be represented. These issues are, of course, particularly important as we're heading towards a post-COVID world. And this is an area where at the University of Exeter, we've also done a lot of work, and we continue to commit to think about what a post-pandemic data science and post-pandemic fair data use can look like. Thank you very much.
Hi everyone, I'm Eliza Duncan. I'm a second year PhD student on the Environmental Intelligence CDT, and my project is looking at natural aerosols in polar regions and how they affect the climate. So when I say aerosol, I'm sure the first thing that many of you think of is a spray can. And whilst this is an example of an aerosol, aerosol is actually a very broad term, just meaning a minute solid or liquid particle suspended in a gas. So today we're going to be talking about atmospheric aerosols. And there are many natural examples of sources of aerosols: volcanoes, chemicals released by trees, dust blowing in the air, and sea salt evaporating from the ocean. And there are also many man-made or anthropogenic examples. These tiny particles have a significant impact on various elements of our lives, from air quality and health, to visibility, to climate, and I'm mainly focused on the climate. But how do these particles affect climate? Well, if we think about increased emissions of greenhouse gases, we know that there's more trapped radiation, which leads to warming, whereas aerosols are thought to have a cooling effect through their interactions with clouds and scattering radiation. However, aerosols are one of the largest sources of uncertainty in climate modelling, limiting our ability to accurately predict climate. And this is particularly attributable to natural aerosols, which is why we focus on pristine regions such as the poles. Aerosols are very complex in terms of modelling. You can see in this simulation aerosols being transported around the world. And in this short time frame that's shown on the simulation, they can cover huge distances. So we really need to consider transport when we're talking about aerosols. So for my project, I'm looking at observations. So starting with a measurement station, for example, Zeppelin in the Arctic, we can measure the aerosols, but where are they coming from? They're not coming necessarily from local sources. They could be coming from a long way. So what we are focusing on is tracking the air to know to find where these sources of aerosols have come from. Using models and wind directions, we can track the air to understand where it came from before it reaches the measurement station. And this produces a trajectory, which is the blue line on the graph. And in order to understand the aerosol sources, we must consider the surfaces that the air passed over. Did it pass over ice? How long did it spend over ocean in this case? But to understand how much aerosol could be produced from these potential sources, we need to consider the meteorological variables. We need to think about the temperature, the wind speed, the relative humidity, the precipitation, and the list goes on and on. This builds a very complex picture, which we can't understand with traditional statistical methods. We need something else. We need a new method. So this is why I'm looking at using AI or machine learning techniques to untangle these processes to help us identify the significant sources of aerosols as well as the processes associated with those. This in turn will help us improve climate models and therefore climate predictions and help us inform policy. Thank you very much for listening.
Hello, I'm Professor Peter Challoner in the Maths department, and I'm interested in how data can be used to look at complex numerical models and how we can make decisions with those models. The world's facing a number of crises. One is climate. We're changing the climate, and we need to know how we're doing that, and we need to know what we can do to change that. But it's not only the climate crisis, there's also a biodiversity crisis, and of course, there's the pandemic. And one common thing about all these problems is that we have complex numerical models that enable us to predict the future from the present day. Those models are very expensive to run. They need the biggest computers in the world, and they will take hours for a single run. Now that means that we cannot afford to do a lot of runs. Now those models are deterministic. If you run them twice with the same inputs, you get the same outputs. But we're never sure about the inputs. There's uncertainty on those inputs, and that gives us uncertainty on the outputs. And we're not sure about the structure of the model either. Our models are wrong. They're not the same as reality. And if we're going to use them to make decisions, we have to take that into account. So the classical way of solving the uncertainty problem would be what's called the Monte Carlo method. We'd sample from the probability distribution of the inputs, and that'll give us the probability distribution of the outputs. But to do that, we need to run the model thousands of times. And if they take 6 hours to run, you can't do that. That's where I come in. What we do is we build what are called emulators or surrogates of the model. So here's an example. There's the model, just one input and one output. I'm just going to run that 4 times at those 4 dots. And then I'm going to build, using some statistical machine learning type methods, what I'm going to call an emulator. And that red line is the expected value of that emulator. It's a probabilistic thing. And the dotted lines are the uncertainty. So it's exactly right where I've run the model, but it's not exactly right everywhere else. But if I now put the model, the true model back on, you can see it's a very good approximation. So it approximates the model, but it gives us a measure of its uncertainty, so we can take that into account. So given we've got this surrogate model, this emulator, we can now do things like predict the model in places we haven't seen before. We can do a sensitivity analysis, see which inputs to the model are important, and we can do the uncertainty analysis by doing that Monte Carlo calculation I talked about before. This now takes less than a second on a laptop as opposed to 6 hours on a big computer, so we can run this thing thousands and thousands of times. So the next thing we want to do is to calibrate the model. We want to take some observations. There's some observational systems there. And we want to make sure that the model agrees with those observations. We don't want a model that's a model of Mars when we're modeling the Earth. So we want to calibrate the model, and here's an example of calibrating a model. And the method we're using here is called history matching. And we calculate a thing called implausibility, which is a scaled distance from the model to the data. So we scale it by the uncertainty. So we rule out inputs that are too far away from the model. But if they're very uncertain, we don't know that they're too far away, so we don't rule them out. So here we've got a region at the left that's not ruled out and a region at the right that's not ruled out. Now we focus in and we do some more runs in a carefully designed way, and we reduce the uncertainty on the left and we reduce the uncertainty on the right, so the left gets ruled out, but the right-hand side is not ruled out because now it's only the data uncertainty that's driving the region we can't rule out. So that's how we could calibrate a model. One of the important parts of the whole process is design. So one of the things we want to do is what are called space-filling designs. We want to fill space with as few points as possible, because every point costs us an awful lot of money. So here's an example of filling a 2D space. You will see it's not at all regular, because we just want to fill space as well as we can. Recently, we've been looking at methods to go beyond that. So you start off by filling space, and then you put new runs in places where you think it's going to be the most informative. So here's 4 different methods of doing that. Ours is in the top left. And the black points are the original points, and the red points are the points we add afterwards. Sometimes we're not just interested in an input and an output, we're actually interested in the dynamics of the model. And this is a famous example of dynamical system. This is the Lorentz butterfly, a chaotic system. And we've been working on methods for doing what we call dynamic emulation, where we actually emulate how these points go around that butterfly. It's a 3D version. And we do very well until we get into the middle of the butterfly, and then it gives up. It gives us huge uncertainties because you can't predict beyond that point. That's where chaos cuts in. So, are the models going to solve our problems? No, they're decision support. So, the models are never correct. They're always uncertain. But if we can quantify that uncertainty, we can give decision makers, we can help decision makers make decisions. Without the uncertainty, it's very hard to balance one model against another. And we have to always acknowledge that the models are models and they're not the real world. So thank you very much for listening. I hope you enjoyed it, and thanks again.
My name's Fiona Spooner, and I'm a senior data analyst at Our World in Data, and I previously worked as a researcher at Exeter University. Today I'm going to talk about the importance of how and where people spend their time, and how we can use this data to better understand the spread of COVID-19. This project was in collaboration with researchers from a number of universities, as well as the gaming technology company Improbable. We used Devon as a case study, and using data from national surveys and the census, we created a simulated population of Devon made up of 700,000 simulated individuals. And for this entire population, we were able to estimate both how and where they spent their time. This information is really useful for understanding where and when the transmission of COVID infections are most likely to occur. There are a number of factors that influence how likely an individual is to be exposed to and infected by COVID-19. A major factor is how you spend your time. If you spend a lot of time in an area with a lot of other people, such as an office or restaurant, you are much more likely to become infected than if you spend the majority of your time at home. How you spend your time is different for different age groups. In the orange on the left, this is how the average person from Devon in their early 20s spends their time. They spend less than half of their time at home, about a quarter of their time at work, and the rest split between other activities. If we compare this with the average person in their late 70s from Devon, they spend 96% of their time at home, with the rest split between transport, leisure, shopping, and other activities. These values are from before COVID and will be different under lockdown situations, but the differences will still be present, even under lockdown. And we see these differences reflected in the number of COVID cases. This graph shows the proportion of each age group that tested positive for COVID in Devon over the course of the pandemic. Age is increasing on the bottom axis, and the colours carry over from the previous slide, early 20s in orange and late 70s in green. We can see that the younger group has had a much higher proportion of individuals test positive for COVID. And as we learned from the previous slide, this is largely because they spend more time in places where the risk of being infected with COVID is higher. As we discussed before, even under lockdown conditions, we would still expect younger people to spend more time out of their home than older people. And this difference is clearly shown in the differences in infections shown here. As well as understanding how people spend their time, it is also useful to understand where specifically people spend their time. If we know this, then we can model how and where people are likely to interact, and therefore where COVID transmission is likely to occur. This map here shows where people travel to go shopping. The black dots on this map show retail points, the white points represent the centre of areas where people live, and the lines show the probability of people travelling from their local area to a given retail point. The thicker and redder the line, the more likely that trip is to occur, and the lighter and bluer the line, the less likely that trip is to occur. We can also do this for schools and to a less accurate extent for workplaces. In our simulated population for Devon, for each individual, we have an estimate of how and where they spend their time. Let's take a look at an example simulated individual in more detail. If we look at the activities section on the left, we can see that they spend 65% of their time at home, 30% of their time at work, and 5% of their time in retail. If we look at retail in more detail and follow that through to a list of possible locations, for example, these could be Tesco, Sainsbury's, Aldi, and Lidl. Based on an individual's location and other attributes, we are able to estimate the likelihood this individual will visit each supermarket. So for example, 75% of the time, this individual would shop at Tesco. So we have the same type of data for workplaces and schools, and all of this data for each simulated individual. This allows us to understand which people are most likely to go to which location, who is likely to interact with who, and therefore where COVID is most likely to be transmitted. We've hinted a lot about how the various lockdown measures could have impacted how people spent their time. Let's look at this data in more detail. The Google Mobility dataset uses mobile location data and shows regional aggregates of how communities spend their time. The plots shown in the graphs here show the amount of time individuals spent in different types of locations, and crucially how this changed over lockdown, which is highlighted in grey. So typically, during lockdown, people spent much more time at home and less time outside the home. We use this data to dynamically recreate lockdown with our simulated population, essentially on a daily basis, changing the amount of time people spent in different locations according to the Google Mobility data. So as I said at the beginning, we worked at the gaming technology company Improbable in this project, and they were able to take our model for COVID-19 and give it a much more usable interface and make it a lot faster. And I'll show you this now. As I've mentioned, we focused on Devon, and those of you familiar with the area might recognise this as the outline of Devon. Each white dot here represents a building in Devon, and we can zoom into this cluster in the centre, which is the city of Exeter. So as the model runs, some of these white dots will turn red to indicate a COVID-19 infection. I'll make these dots bigger to make it a bit more obvious, and it will run very quickly, so watch carefully. Okay, I'll start it now. So in just a few seconds, it has simulated 3 months of COVID outbreak, and you can see the plots on the left show the number of people in each infection stage across the 3 months. So just to recap, data allows us to understand how different people spend their time, estimate how and where people interact, and therefore predict the spread of infectious diseases. Thank you for listening.
Hi everyone, my name is Karen Morrissey, and we're going to launch into the broader panel discussion around the question of using the power of data to create to create solutions for a green future, many of which our presentations have already touched upon. But now you guys have an actual chance to hear from the experts their own personal opinion based on their work. So I'm going to briefly introduce our panelists. We have Fiona Spooner, and she's a data analyst from Our World in Data, with a background in using data science to investigate and understand the impacts of global change. And you've just seen her presentation. We have Sophie Gumi, is a technical officer in the Department of Environment, Climate Change and Health at the World Health Organization. We've Tam Minonier, who is actually maybe the one participant who you haven't been introduced to so far. And Tam is a research fellow, and she's using big data, and I mean seriously big data, to look at domestic energy and indoor environment, and to link it to how this can potentially impact on our personal health. And Ellie Duncan, and I have to tell you, I actually, when I heard about Ellie's PhD, I straight away emailed her and said, oh, we're doing stuff on aerosols, but yes, I did think about the ones in cans, but sorry, Ellie. Ellie Duncan is a second-year PhD student on the CDT for environment intelligence. So we really great to have all of you online and willing to chat about your research in terms of how we can use data to create a green future. I'd just like to say that I'm not sure, hopefully it's not glaringly obvious and it can be just taken as a given, but all the panel, including myself, are women and identify as women. And this wasn't a ploy or, through the lens of, this is actually the people that we selected based on their research. So it's really amazing to see so many strong females working in the data science community, and long may it last. So I'm going to put out a question to our panelists, and each of you will have a chance to respond. And my first question is, we've heard so much about big data, and big data is just apparently going to change the world. But for a lot of us, we've already been working in big data for the last 10 years. And, we're doing good work, but, how is it going to change the world? So what I want to ask you guys, based on your experience, is what does big data offer to our research on building a green future above and beyond traditional approaches? So, what is that extra mile that we can go with big data if policymakers were willing to listen to us? We'll get to that in a while, maybe. Over to you. Do you want me to pick go one by one? Okay. So clearly none of you are actually Irish and chomping at the bit to speak. So I'm going to go first with Tam, then perhaps Sophie, then Ellie, and then Fiona.
So thanks, Karen. Yeah, of course, as we've seen, the more data that we have, the better picture that we can build. So we can have big data that cover a broad range of situations, and focus in on a single situation. And of course, we can have different types of data that are integrated together, which all combined gives a kind of broader, deeper picture of a situation. So in my work on Smartline, the sensor data we have provide moment-to-moment monitoring of a situation, such as energy usage, temperature, air quality, and that high resolution, the high temporal resolution in the data opens up the possibilities for understanding the dynamics of the processes, excuse me, that are not possible to see from averages or perhaps other more traditional approaches. So for example, when humidity is high inside a home, it's not just a case of switching on a fan, but we can take into account human comfort, the temperature, the time of day, and be able to model the effect or predict the effect that an action would have. And so by doing that, we can see the minimal intervention needed to mitigate the issue, the high humidity in that case, which could be used in smart control systems to energy to allow greater energy efficiency. But we can also aim to avert the human responses that might otherwise counter that change, such as people switching off the fan because it's cold or noisy. So overall, for my work, the big data brings a more detailed and integrated picture, and I think allows more targeted solutions.
Thanks, Tam. That's really interesting. What strikes me is that even though you're using big data, which is sometimes seen as a way of taking humans out of the loop, you're feeding directly back to humans and helping them make choices based on data. So really great. Sophie.
Thanks, Karen. Okay, unlike all my co-panelists, I am not a researcher, so I'm not going to talk about research or from a research perspective, but more, working in WHO, we are more at the interface between using the data and how we can use it to inform policies, right? So I think a first point I'd like to make, which has to do with what I'm working on air pollution, is the fact that on air pollution and health, we have been using really proxy indicators for a very long time. First, there were very few data, as Gavin has shown in the presentation. We have very few input data, and even this input data was not really, exact. It was really a proxy exposure. It was ground measurement, and ground measurement, they are not really representative of people's time, time activity. And the big data, it opens a huge new way on how we can really follow up time activity patterns for people, and how we can measure and monitor their exposure, and in turn how it can be used to inform policies, to really try to really target vulnerable populations and having really specific dedicated policy for vulnerable populations. So I think for this opens a new way, which is really incredible. A second point is the citizen science and the use of local sensors that is producing this big data. Then we need a different type of skills because we have been constantly telling countries, okay, monitor, we need data. But with big data, you have the data. Now the most difficult part is how to process the data. You need a different type of skills to analyze all this data and to process this data so that you can use it. So I think it opens a different way of working. So for sure. And then another point I'd like to raise, just the last one, is related to things we have heard also from the presentation, was the Copernicus and all the satellite data that we have now at hand, that gives us also a huge information on the source of the data. So it's very important for policy making, because once you identify the source, you can target your policy and your intervention. So I think this is huge, but there are a lot of drawbacks, and we have to put safeguard in place so that we can really use the data, because there is a big problem on data access, on criteria, how to choose the data. I think a lot of countries, it's overwhelming, all those information on data, and for you scientists working on the field, it is, as you said, it's not new, but for the end user, it is impressive. And I think we will need some time to figure out a nice framework on how we can really use this data. Yeah.
Thank you, Sophie, so much for that. And yeah, I guess I take for granted that big data has been around for a long time, but for most people, it's quite new, as Laura said, even in the health world. So it's really great to have you here with us today, where you're really bringing it all together, reminding us of researchers what we need to do to go and speak to the policymakers. Ellie.
Yes, so when we're talking about the Earth system, it's always the case that we have big data because it's such a vast, complex system. But what I think is quite exciting going forward with big data is using this wealth of data that we have from satellites, from ground observations, and also from models, and combining these to help focus and improve the understanding of these processes that we still don't understand. So for my work, looking at aerosols, and so then if we can improve our understanding of these physical processes, then this will help us inform policy, because we will have a better understanding of how the system works.
Sorry, thanks, Ellie, that's really great. And I'm just over to Fiona.
Sure, yeah, I think, everyone's covered a lot of really good points there. I think, so I think the main advantage big data has over traditional approaches is that traditional approaches are just snapshots. You often spend a lot of time and money and effort and like person hours getting surveys, and you might do them just once a year or once every few years. Whereas big data, if you can set up a sensor system, you can get a continuous stream of that data, which I think that is the main advantage. But I also think they're not mutually exclusive. So traditional approaches, such as surveys, if we can pin a lot of them together, we can kind of create big data. And I think a really good example of this, in biodiversity at least, is the eBird program, which essentially people have been collecting data on where and when they see birds for centuries. But eBird kind of provides an infrastructure for pinning that all together, and using that, they've essentially created big data from small data, I guess, and they use that to create really cool tools. You can now have much more detailed maps of where bird species are and what their abundance estimates are. And this is really useful for conservation planning. So I don't think they have to be mutually exclusive. I think they can work really well together. And yeah, I'd like to see more data integration like that.
Message received, Fiona. This is something I'm quite passionate about, is that we need to make use of all data, and all data should has a place within the wider discourse around big data. So that's one of the reasons I try to use data science rather than big data and whatnot. But yeah, thank you for your great responses. I'm mindful that time is going really, really quickly, and I want you guys to think about to respond to my next question, which is really the big one. And what is the next step for big data in building a greener future for you guys? Sophie, would you mind if I took you first, just from let you go first, just because you have the perspective of the policymakers, and we all aspire to work with organizations like the WHO. It's the holy grail for researchers.
Thanks. But my contribution is more modest, right? Okay, now a quick and few. So I think what I said before, I think it's important, first of all, to also define all this different terminology is different from the traditional data science. So I think having an agreement among the scientists about a clear definition, what is big data, having something very clear and agreed upon, this is important. First, so second, having a framework or criteria of what we can use, what is quality control, if you wish, or something that countries can really say, okay, I trust this I don't have to put doubt on this, right? Because this is something we have been facing even with data, even we were receiving traditional data from countries, and even these countries were again back, they were not accepting this data easily, even though we were telling them, look, this comes from you. So I cannot even imagine now if we have all this new big data, all these different sources, I think it's very important to have a criteria and having a framework where this data feeds into it. Another point is also then I think it was mentioned before, it is the ethics, the equity, and the open access to all this data, and ensuring confidentiality. So I think this is also a big part of this data, because there is a lot of countries are also, there is a fear about this. Is a bit scary, big data. So I think trying to find a framework where you can really address all those different issues, definitions, criteria, how to select, having like a grading of the data, how you can use it. This is something very important, because data input, this is crucial, and data input, this is, you're a scientist, so it's the gold, right? If you have the data, you have the power. So I think this is why this is also a little bit scary from sometimes. So I think that the future is really trying to put like a frame, to put all this data into a frame.
Yeah, I really agree. Actually, I'm going to bring that question to Ellie now, because Ellie, as a PhD student, is our most embryonic researcher. And when I asked her about what she'd like to contribute, she said, oh, I don't know if I've anything to contribute, given that I'm only a second-year PhD. And they were her words, not mine. However, I want to just reinforce, Ellie, that actually it's our PhD students that do the most innovative work. And I think having a view of where you think the future is going is the most important. So over to you. No pressure. Sorry.
Yeah, thanks for that introduction. I think that, yeah, it's going to be really important to make sure that we combine these different data sets that are out there, because there's so much data, there's such a wealth of data. And if we combine these data sets from different sources, then hopefully this will offer us the opportunity to explore different relationships, for example, in the Earth system or in health, and just really combine the data that's already out there. And I think, novel techniques are going to be quite important in this process. Dealing with so much data is quite hard with traditional statistical methods. So I think machine learning and AI is probably going to be the way forward.
Really excellent, thank you. Tam.
Yeah, so I completely agree with Ellie there as well, that the next step, and it's been alluded to throughout the whole session, about bringing the data together and integrating the data. It's kind of really important into building up that big picture of the situation. But obviously it's difficult, and processes are needed to learn how to do that and share practice in the best ways to do that. For me personally, in my research, we've seen that we can identify behaviour changes during the COVID-19 pandemic, looking at sensor data in the home and utility usage. And so the next step for us is to develop methods to spot other behaviour changes or issues with the building, and those kind of things. And those methods, as they become developed, could be applied to other situations, that could be applied to energy efficiency and so on, moving forward with green practices, or they could be used to identify behaviour change in response to environment, energy efficiency education.
Thanks, Tam. Fiona, you've spent the last year wrestling with all sorts of data from all different sectors. So I know that you have very strong feelings about standardization and the need for a framework. Is there anything else that you'd like to offer?
I think the only other thing I would add is that there's obviously a huge amount of data that's freely available. For example, like remote sensing data and all sorts, but it is quite hard to access, in the sense that it's quite hard to find. And also when you do find it, it might be quite difficult to use. You might need a certain set of skills. So I think in order to kind of really maximize our ability to use big data for a green future, we need to make sure there's more people educated in data science, and that we have those skills coming up just from a school age and all the way through, so that we can use this data, because it's clearly not going away, and our need for it is also not going to go away.
I totally agree, and let most of them be women is my opinion, but some clear messages coming out from our panel in terms of how the data can be used. So we're awash with data, that much is clear. What we really need now is maybe to take a step back from the actual data and think about how to build consensus and frameworks about what we value as data and what meets these standards. So in a way, we might be post-techniques and actually going somewhere into the more sort of gritty governance, legal aspects, which Sabina spoke about in her presentations. But I'd really like to thank everybody for their time. It was a wonderful panel, and lots of food for thought. Back to our, I think it's Gavin, back to Gavin and Jessie now. Thanks, everyone.
Thank you, Karen, and thank you to Fiona, Ellie, Sophie, and Tam for a fantastic panel session. Very much food for thought. And now we're going to move to our workshop on looking at how we might visualize and better understand the risks associated with climate change. And so I will now share my screen. And hopefully We should now see PowerPoint title screen, Climate, the Climate Impacts Mitigation, Adaptation and Resilience Framework. And I wonder if I could ask my colleagues, Jesse Abrams, Fiona Spooner, and Matt Thomas, if they could say hello. We're going to run this hopefully as a series of interactive parts of the session in which we'll all be able to investigate some climate projections data and how it might interact with different areas. And our case study, you might not be surprised, is not Devon this time. It will be starting with Cornwall. So I think we're actually a minute ahead of schedule, but I'll continue anyway, I think. So welcome to this interactive workshop on CLIMA, the Climate Impacts Mitigation, Adaptation and Resilience Framework. This work is done in the Joint Centre for Excellence in Environmental Intelligence, a joint research centre recently established between the UK Met Office and the University of Exeter, with the aim of pioneering work in environmental intelligence, the use of data science and artificial intelligence, and integrating that with environmental data and crucially environmental expertise to develop methods for solutions to environmental challenges and climate mitigation and adaptation, and also building a green future. So the impacts of climate change are far-reaching and destructive, putting people, businesses, and critical infrastructure at risk. And the climate risks are determined by how vulnerable we are and how our surroundings are when exposed to climate-related hazards. And we'll see in the examples today that the framework of CLIMA is built around when there's a hazard, which might be increased heat in an urban area. How does that interact with people who are exposed to that hazard? How much time do we spend indoors or outdoors? And actually, if we are exposed to that hazard, how vulnerable are we to that hazard? So in the case of heat and human health, age would be a risk factor and pre-existing health conditions. So climate impacts, or the risk of impacts happening, is the combination of these three things: hazard, exposure, and vulnerability. And in CLIMA, what we're aiming to do primarily is to look at the intersection of hazards when they expose individuals, or if they're human beings, or assets, if they were electricity substations or telecommunication networks or transport systems, for example. And given that a person or a being or an asset is exposed to a climate-related hazard, how vulnerable are they to it actually having an effect? So we would define impacts as actually something happening, normally something that is not particularly advantageous, and then we would look to estimate in CLIMA the probability that those impacts occur by looking at the intersection of hazards in a particular area and also the vulnerable population or vulnerability of certain assets. So if we think a bit more about hazards, I've mentioned a few times the idea of increased heat in urban areas. We might also think about the potential for increased precipitation as our climate changes, which might bring flooding. And in other areas of the world, perhaps in the UK, we may have problems with drought. Also, the CLIMA framework applies equally to other environmental hazards, such as air quality. If we know where emissions of air pollutants are, then we can look not just to see what concentrations are in any particular area, but actually who are exposed to those concentrations, which members of the populations will be breathing in that unsafe air, and actually how vulnerable are those people when they are exposed to high levels of air pollution. So in this presentation, and when we look at the interactive apps to investigate the hazards, exposures, and vulnerabilities, we're going to focus today on urban heat. And in particular, we're going to, or rather increases in heat, and we're going to look at some climate projection data produced by the Met Office, which is known as UKCP 18 data, UK climate projections data. And here's an example. This really is a large data set, which is an output of a very complex series of models. And it covers a number of climate-related hazards and variables, including winds, precipitation, and temperatures. We're going to focus on temperatures today. And here we have projected temperatures in Bristol over the next 50 years or so. And these show the average monthly maximum temperatures in the Bristol area, going from in the 20s in the 1980s, increasing through the 2030s, and then showing some quite marked increases in 2060 and 2070. It should be noticed that there are obviously a great deal of uncertainty associated with predicting climate and weather-related variables into the future. And there's a whole series of model runs within UKCP 18 related to different RCPs. And this is the most extreme one. So these rather marked increases are at least associated with the most extreme scenarios known as RCP 8.5. But it gives us some idea, two things. One is what the hazard we're focusing on now, which is maximum temperatures, might change over time, and also a very initial example of how we might be able to look at those changes in climate and in this case temperatures at local areas. So what we've done here is extract the Bristol area from the UKCP 18 data set, and we've then processed that data to come up with these estimates of average monthly maximum temperatures over the coming decades. And at this point, I'll ask you all to, if you have a web browser open, you can join us in investigating those hazards within the United Kingdom. I will put the link into the chat now, and then I will stop sharing that screen and share this one. So hopefully no, I'm afraid it's not liking me sharing a specific screen, so I'll do it a little more manually. Here we go. So this is the first of our interactive apps, and this shows us in Cornwall the maximum temperature data for different months, looking at different years, or actually different decades. And we can see here on the first example, we've got Cornwall. The blue distribution shows us the maximum temperatures within the decade 1980 to 1989, and the second decade shown on the app 2020 to 2029 is represented by the red distribution. And you can see for each of the months that generally maximum temperatures are expected to rise, or have risen between the 80s and the decade we're in at the moment. And then we can use the app to pull down and compare for different decades. So if I wanted to compare the current decade with what the projection is for 2060, I can use the pull down menus, and I can see that those differences actually become more marked. So the temperatures are expected, as we saw for that example in Bristol, are expected to increase certainly in the summer months. And I think this would be a good time maybe for our participants, if you would like to have a investigation maybe of temperatures in your area to see if you see any trends. If you pull down the menu on the right hand side, these are local authorities within England, and you can see what the changes might be in other areas of England. So at this point, I'll see whether people would like to have a play with the app for a few minutes. If you have any questions about either using the app or any questions about the data that goes into the app, or anything to do with thoughts you might have about the integration of hazard, exposure and vulnerability, please do put them into the chat, into the Q&A, sorry, as we go along. And Jesse and Fiona and Matt would be more than happy to try to answer those questions, either technical using the app, or more generally, we can call on Jesse's expertise on climate projections to help us with questions related to the underlying data. Okay, so I think we'll leave maybe 2 or 3 minutes for people to investigate using the app, and then we'll come back in say 2 or 3 minutes time and discuss what we might have found. And I suppose if there's an exam question to be answered, it might be, what does the climate projections in your area, assuming you're in the UK, if you're not, then choose an area in the UK, what changes in maximum temperatures might we expect over the coming decades, and then to start thinking about how that might actually impact the way we live and how we might adapt to these changes in our climate. Well, I'm not seeing any issues in the chat. I hope I don't anyway. So I'm assuming that people who do want to play with the app have successfully managed to log in and are investigating the underlying data. So I think we'll. Oh, there is just one question actually. Apart from thinking where you might book your summer holidays. Why does it look like the temperature is going to vary so much in August compared with other months? And I might actually see whether I could just ask that question of Jesse. Jesse, if you're here and fancied having a stab at answering the question, why might different months vary? And maybe you could say a few words about the underlying UK CP18 or ICPs.
Hi everyone. So Gavin mentioned the RCPs. These are what's known as representative concentration pathways. They are basically scenarios for different greenhouse concentrations in the atmosphere. And they're 4 standard scenarios that vary based on the amount of emissions that are predicted. The other part of the question was, why is there so much variation? As the climate warms, we will probably see more extremes in both highs and lows, potentially. And the UKCP data that's shown here is based on multiple models. I think it's an ensemble of 12 or 15, not quite sure there. And there's large variation between the predictions here. So that capture some of the uncertainty that we have and where the climate will be heading as emissions continue.
Okay, thank you, Jesse. I'm minded that as with much of this afternoon, we're trying to get a lot of really important information into a short period of time. So I'll move on with the second part of the presentation of this climate workshop, and that's now we've thought about hazard, and now we might think about exposures. So in the case of heat or increased heat and human health, but we can imagine that it's not just human health that heat will affect, but a range of other things that might affect the way we go around, we spend our daily lives and the way we work and the way we move around. But let's think about the effects of heat on health. We need to know who is exposed to that heat, how many people spend their time outside, and what activities do they do. Now, not everybody will be able to afford air conditioning, and to be honest, if everybody started using air conditioning, that would pose a whole other range of problems related to climate change. But let's imagine for exposure, we think about location, where people spend their time. Do they spend their time in hotter areas, cooler areas? Do they have access to green space? What activities are they doing? Obviously, it might not be advisable to go running in very hot, humid weather, but there are certain people, their occupation means that they will be outside, or will it be too hot to do certain occupations at certain parts of the day, in certain parts of the year. So along with exposure, let's imagine people are exposed to these increased temperatures, sorry, then how vulnerable are they? And that's going to be a very complex mixture of previous health conditions, also age, and what we really need to do, of course, is to see how a hazard will impact on different people and different members of the population, and try to establish, are there any groups of the population that will be more vulnerable to climate change? And then we can hopefully start to understand some of the inequalities and address those when we're looking at mitigation measures. So we've got hazard, exposure, and vulnerability. And just before we go to our second app, this is really the kind of crux, the central component of climate, which is to integrate data from multiple sources. We've seen data from UKCP 18 projections for temperature, which is actually on a gridded basis, and we've converted those into these spatial areas, MSOAs. Also exposure, that exposure data, occupation, and where people spend their time will come from very different data sources, and we need to be able to integrate that with hazard data. And we've seen throughout the presentations and the panel discussion today the importance of data integration, of data quality, of understanding where the data's come from, but also to understand ethical and societal considerations, and to put this into the context of actually using this in a way that might affect people's lives. And also knowing whether there's a hazard and whether people are exposed to that hazard, we need to know the vulnerability, which will really tell us how serious the impacts will be. And so the example we'll look at now, sticking with temperatures, will be to look at, instead of increasing temperatures in a comparison between decades, we're going to look at maps of temperatures. These are the maximum temperatures for, I think it's 2060 in the southwest for different areas, and we'll see that we can overlay those temperatures with measures of exposure and vulnerability. And what we've got in our second app for you to hopefully enjoy is an app that allows, and here's the link. It was in the chat already, but I'll put it at the bottom here and send it to everybody. And so here's our second app, which is a rather simplified version of exposure, vulnerability, and hazard, but hopefully it'll give us an idea the kind of power of climate to integrate three. So if we think about exposure, in this case, we've taken a fairly simple measure, which is the population in these MSOAs, middle super output areas. And we'll see that there are some areas that in the southwest that have higher population. And then we were trying to think of a nice, easy to understand measure of vulnerability. And of course, it's not restricted to this. Having the flexibility to use different measures of exposure, different measures of vulnerability, and indeed different hazards is one of the major advantages in the Climate network, because it's built around this data integration from different sources and then a probabilistic model to come up with the impacts. Vulnerability in this case, we've just looked at the proportion of people in those areas who are over 75 years. We saw in one of the presentations earlier that was based on a synthetic population of the UK, and actually we have additional vulnerability information that we could use at this point, including linking it to the Health Survey of England to give us information on previous medical conditions. But what we can do in the map is to overlay those two maps, and then we can see the kind of areas where exposure and vulnerability might be high. And of course, behind that, what we really want to do at the end is to integrate that with hazards. So we've taken the UKCP18 data, maximum temperatures for 2060, that we saw in the previous app, and now we've put them in map form, and we can see that temperatures are expected to rise over the whole of the southwest, with the end of Cornwall, where I am at the moment. Actually, I'm right down here today, showing some marked expected increase, at least under this this particular scenario. And then what you can do is to overlay hazard, vulnerability, and exposure. And then what we're really interested in, of course, is where there's an increased hazard, are there any areas where there's also increased vulnerability and increased exposure? And those might be the areas where we need to focus most effort in adaptation. And also, they would be the ones in climate that would come up with a higher probability of an impact, where an impact might be increased hospitalization or hospital admissions or increased mortality during heat wave. As with the previous app, you can pull down the menu and you can look at the effect in different areas. We have regionalized this, and you can see that certainly in the case as we go further north, if you remember the colors, the increase in temperatures aren't going to be as high as in the south. But again, there may be areas where there's increased temperature. All of these orange colors with the increased temperature, and we can see whether they also interact with areas that might be expected to have a high proportion of vulnerable individuals. So unfortunately, time doesn't leave us much chance to play with the app now, but if you have any questions about the app, please put them into the chat. And I'll go back to the slide deck and give a final summary on climate. We've looked at an example of heat and human health, and we've looked at some relatively simple proxies for exposure and vulnerability. Also, we have only looked at increases in temperatures. What we also would want to do is look at temperatures, humidity, and other effects that might have an adverse effect on health. Other applications of climate are the effects of flooding and heat on critical infrastructure, for example, telecommunications networks and electricity networks. So, for example, with increased precipitation, hotter, wetter summers that might be expected, would we expect to see more flooding in certain areas? Where would those areas be? And how does that flooding interact with our homes, for example, or with roads and railways, but also with the kind of infrastructure that keeps the country going, like power networks and telecommunication networks? Also, looking further field in time, climate change and energy security, with an increased reliance on renewable energy, changes in our climate, we need to make sure that we are planning for those changes. Some might offer opportunities, some very much might not when we're planning future energy strategy. And the other thing is, climate, we've looked at long-term changes in the climate, the underlying mechanism behind climate, which essentially is a data integration mechanism with this model for estimating the impacts and also the probability those impacts happen, can be applied both in the near and the longer term. We've looked at long-term climate changes, but we're working on examples where it could be on a shorter term basis as well. So many applications of climate, and we'd be delighted if you would like to talk to us about climate, either the applications we've shown or the potential for climate to be used in different ways. And we would be delighted if you were interested, in which case I suggest that you contact us on our webpage, which is www.jceei, Joint Centre for Excellence in Environmental Intelligence.org, where you can find more information on the Joint Centre itself, and then there's a special page for the climate project. Thank you very much. And now I think it's back to me, the presenter, just to say a big thank you to everybody who's participated in this afternoon's event. If you are still here and with us, could I ask you to put your videos on to all wave goodbye? So thank you very much, in no particular order except for the circular bit on my screen: Laura, Ellie, Tam, Karen, Sophie, Jesse, Fiona, thank you to Matt for putting the presentation together. And also, she hasn't put a camera on, but I'd like to say a big thank you for Kitty for pulling this event together and for making sure that we had the opportunity to present our work today and working with us to make sure that it went as well as it did. Thank you very much, everybody, and have a fantastic weekend.